Welcome to the another session in Frontiers in CFD. So today's topic is CFD simulation of lithium-ion battery with composite phase change material and liquid cooling. Today's objective is to prepare the 3D geometry of lithium-ion battery pack with PCM and fluid flowing through the tubes. Again, to understand the heat generation per unit volume and the effect of fluid flow. Last objective is to apply the boundary conditions and visualize the results. So this is the geometry which we are going to follow. We'll be using the heat generation rate of 104017 watt per meter cube. This is taken from one of the reference paper. So the title is also mentioned here. Uh, these are the dimensions for the we can say pack. Cell diameter is 18 mm, and accordingly the remaining dimensions are there as per this image file. So you can join the channel in order to get access to geometry file, which will involve only geometry. If you required any consultancy support for CFD, so you can go with the second option. Third one, if you just want the image results of the simulation which has been done, you can go with the third category. And last one is the access to setup file. So this involves complete setup right from the geometry, mesh, then setup which has been done, and lastly complete results. So the last option, it involves everything. So this will be a file which is shared in the form of Google Drive, a link which is to be run on the version which is run currently and higher than that. Thank you. Geometry we already have prepared, so I will just quickly go through the geometry and have a visualization of the geometry, and accordingly we proceed further. Next part that is related to generation of mesh and generating the results. So this is the geometry which we have prepared. So we have this battery pack uh, which involves tubes also which are flowing over here. In addition to these tubes, so any one of them will be inlet. So this one is, let us say, inlet for this. Similarly, inlet for this it will be here, and this will be outlet, and this will be outlet for the other piece. So the cells are there within the structure. So we have defined the materials also, like this is the porous material which we are having. Then aluminum casing for the cells. Then we have the cells. Then copper pipe, and this last is the fluid. So these are some of the operations that has been performed in order to prepare the geometry, and accordingly we are going to proceed for the simulation. So let's go with the fluid flow fluent. I will just try to generate the mesh here. So let's click on this. So regarding the details of the geometry, so this is how the details are there. So you can, for the box dimensions 180 in x direction, y direction is 60, and z component is 150. So box dimensions are 60, cell dimension will be equal to 65. So accordingly, the geometry has been prepared. So this will be a tube, and through the tube there will be a fluid which is flowing. So that has to be separately defined, and that is also to be specified in the geometry. So let's, next part will be generation of mesh. So we'll try to generate a little bit finer mesh so as to produce it uh, correctly, because the fluid flow simulation will be there, and that's why it is important to keep the mesh size smaller, especially in the zone where the fluid is actually been flowing. So right now, if you see the statistics, it is around 4,73,613. So we might not prefer to go with this mesh. I will just go with 0.001. We'll just check it how much it goes. Let's generate it. A comparatively finer size of mesh will ensure the problem of Poran number will not appear. to select a proper time step size also. Okay, so this is around 100% is there. So quite better mesh. So it might take some more time. I will just slightly go with 2.5. We want to keep the time also within the limit, so that's why let's check it for 0.0025. How much number of nodes and element it comes. Okay, so this looks to be 5,49,109. I may prefer to go with something, let us say 1.5. Let's make it generate. So we took the element size as 0.0015. So let's see what. Okay, so this looks to be slightly better than what we had earlier. So, okay, so let's proceed with specifying the inlets and outlet. So this is our XY. So I will say this is one of the inlet. Okay, just a minute. So I selected two faces, so that will be both are inlet. Similarly, I will select this one, and the other one. So I select this, make it outlet. So this will be inlet and this will be outlet. There are two faces for us, inlet and outlet. So in addition to that, I will just go with geometry. So casing, I will show hide all other bodies. So I'll mention this is casing convection. Next is, so this is inlet outlet and this is casing convection. So we need only three. So I will just keep it with only three. So any part of that, we'll say if it is required, we can put, but I am keeping it only three. So make it update. So mesh translation to fluent, this successful message will appear. Okay, so this message appear. So I'll just try to save the work. say. So porous material with PCM pipe inlet and outlet. So this is what I'm giving as a name. So any name you can give. Okay, so save it. So once this is done, you can actually close the geometry part. So let's close the geometry, and even you can close the mesh part also. So let's go with the setup. Click on edit. So I just put number of cores as per the computer configuration. So we'll be using the paraffin wax as a PCM. Lithium-ion batteries are already there. Then aluminum casing will be there, and so this is the copper pipe. This will be the materials for us. So let's make it. Okay, so you can see the inlets and outlet. You can actually just confirm whether how the things have been done. So accordingly, you can proceed. So the geometry is there, and now let's specify transient. Put it gravity. I'll put it minus 9.81 here. Model I will make it energy equation on. Make it okay. Viscous I will take K epsilon. Enhance wall treatment, thermal effect, curvature correction. Make it okay. Then solidification melting is also required. So put it okay. Then materials, I will specify the materials first. So first we are going to specify as a paraffin wax liquid. So chemical formula again I am just writing paraffin wax liquid only. So use the density. So this is taken from one of the reference paper 790. Specific heat 2150. So these are all for liquids. 0.22 as a thermal conductivity. Viscosity is 0.01. Pure solvent melting heat 240 800. Solidus temperature I will put 313.6. Liquidus temperature I will put 317.7. So make it okay. Let's close this. So another fluid that we require is water liquid. So I will just directly take it from the database. So make it copy and then close. Solid, I will just put it paraffin max solid here. Okay, so just put the values here. So 880, then CP is 2000, and thermal conductivity I will put it as 0.2. So make it change rate. Okay, close the window. One more time, I will just go with the other materials what we required is the solid, that is we required aluminum. Make it copy and close. Let's close. one more metal which we required is the copper. So make it select and make it copy and close. So for lithium ion, I will just rewrite here lithium batteries. So I'll just put lithium battery here. So let's put the values, that is 2750, then CP 1250, thermal conductivity I will take 1. So this is taken from one of the reference paper. So one more thing which we'll add is the aluminum. So let's go with the aluminum and make it copy and close. So it's all the materials we added. Now accordingly we'll proceed for the next part. So let's go to the cell zone condition. I will select zone type. So fluid, this will be your water liquid that is flowing. So mention it as a water liquid, make it apply, then close. Then porous material, I will select the porous material as the paraffin wax liquid. Here I will specify the porous zone. In porous zone, I will specify the porosity. Let's put a porosity, I will put it 0.9. And I will select the material, as a copper. So copper metal composites are there, so that's why I selected that. Aluminum casing will be as it is. You just need to ensure the material with what you are selecting. So these are all solid part which you are doing. Then cell. So cell will be your lithium batteries. Make it apply and close. And copper pipe again, make it copper and close. So material section actually done. Now let's go with the boundary condition. So I will just put some value of velocity here. Say 0.05 meter per second. That is the velocity at inlet. So whatever both inlets are there, so accordingly it will be there. Then I'll go with the okay, so I will just go with the casing convection part. So all aluminum casing I will go. So I'll put the convective heat transfer coefficient here. So let us say 2. This material you have to select. Let us say it's aluminum. So make it apply and close. Wall cell again you have to select the material. So we know it is lithium batteries. So I'll go with the lithium. Other thing I am not changing. Wall copper. So this is also the material that has to be selected as a copper. Make it apply close. Then wall porous material. So okay, so let's specify the report definition. Now go to the new surface report area weighted average. So I will select temperature here or solidification melting first. So where the solidification melting has been taking place, so that we need to carefully select. So I will just slightly take this on the side so as to visualize everything. So solidification melting will happen in the porous region. So I will select that region only. So porous material. So this is a porous. So this is a porous and this one. So that will be more accurate if you select only porous material here. This is again porous. Okay, so I selected all porous material, and so similarly we'll see this one also to be the porous material. So make it okay. So new area weighted average. So I will set to temperature. I will put a total temperature. So I will select only outlet. So this is the outlet. So I'll mention here total temperature at outlet. So print to console, make it okay. Okay, so first thing, yeah, I will just edit the first part. This one, report definition edit. Okay, new surface report area weighted average. So I will put it one more time, solid from liquid fraction, print to console. Then I will mention here solidification melting. So I will select only porous material here. So this is a porous material. So whichever you will see the porous material, that only I will select. So this is porous. This one porous. Okay, so wherever you will see porous region, that I will selecting. So make it solidifying melting. Already I have not given the name, so that's why I'm doing it again, and I will delete the old part. So these are the two things which is done. And solidification melting, total temperature outlet. So this one I'll make it delete. Okay. So now let's new total temperature we have taken at outlet. So I will take it total temperature of the body or system. So make it here and click on total temperature. Make it okay. Then close this. So this is the first which we had. I don't want this. Okay, so I deleted the other one which we did it first. So go to the initialization, click on initialize. You can actually put it compute from inlet, but not an issue. So make it initialize. Then go to the calculation activities, save it 20. Go to the solution animation, new object contours. So I will select first one solidification melting. So again I need to select the region only, whichever having the porous material, so that region only will select. So before that let's make it float. Okay, so select all the porous material regions only. Okay, so here we have porous material, here we have porous material. So wherever you will see porous material, that only will select. If you are not selecting the porous material, there are chances that the solidification melting curve will not be related to the porous region. So we have selected all. So accordingly, we will now proceed with the next part. This is also one. Sorry, this is left. So ensure that each and everything is selected related to porous material, and last one we had at the bottom. So make it save display. Make it close and select this as a solidification melting. So make it okay. So here again I will just go with a new object, then contours. So instead of solidification melting, now I will select temperature, select the total temperature here. Instead of exponential, make it float, make it apply, close, make it save display, make it close. This is contour. I will specify as total temperature, make it apply. Okay, so one thing I think was left was cell zone condition. Cell I will specify as the source term here. Go to the edit, specify the source term. I will put some value. So there are various C rates which are available. So out of that we'll select the C rate which corresponds to 2C, and there is 3C also. So 47579 we can put it for 2C, and if you want it for higher we can put it, let us say 104017. So this is for C 3C. Make it okay, make it apply, make it close, and one more time I will do the initialization because this was left. So I just forget to put the value of cells source term in the cell zone condition, so that's why I did it again. So go to the this one, put it around 10. We'll just check it for 10 and then we'll proceed further. So C rate we took around 104017, that is corresponds to around 3C, and let's check what will happen here. So as the mesh size is comparatively smaller, it can take some time for the iterations, but as we have the rate which we have considered as around 3C, so we might visualize comparatively higher temperatures in the region. So our aim is to visualize the solidification melting, as well as we want to visualize how the fluid is flowing from inlet to outlet, whether there is some rise in the temperature of the fluid or not. So that is the thing which we are interested in, and that's why we put certain curves in terms of the total temperature curve. Then we put the curve for total temperature at outlet. Then in animation we set the solidification melting. So all these things will be visualizing during the simulation. So you can always check the usages based upon that, the time required you can have. So almost 22 GB of RAM is actually already been utilized, and CPU usage is almost 100%. So that's why it's taking some more time. So once the temperature contours and other things are visible, you can run the simulation for longer time based upon we say the requirement. Let's say if you want to run it for 600 seconds, or if you want to run it for 1000 seconds, and so accordingly these values can be specified there. So we are having 10 as a time step and time step size 1. So the simulation will be for 10 seconds as of now. You can put higher value 100, 200 and so on. Accordingly the iterations will be performed. If there is a problem of current number, you have to go with the other adaptive time step, and you have to reduce the time step size also. Okay, so that these curves are actually been now visible. So one by one we'll quickly go through it. So first is the residual, second is your total temperature. This one shows the solidification melting. So as of now the curve is at 0, so nothing has happened because the melting has not started. Average temperature, you can see the rise. Then this is the temperature contour and the liquid fraction, which is not there as of now. So we'll have to wait for some time. Once this calculation is complete, then we'll continue further. You can see the changes in the color contours. So we have to wait till all the time steps are completed. So we'll preferably run it for around 100, 200 or 300 seconds, and we'll visualize how much temperature variations are there. So we are around the end of 7 time steps, which is we are specified earlier. Now you can see the temperature rise which is in there. So it is rise by around 0.21. Red zones are being observed over there, where this heat generation is taken by the cells, and along which we observe some blue zones also that indicates the comparatively lower temperature. So we had tubes which are flowing, tubes which has the fluid which is flowing from inlet to outlet. So let's visualize the total temperature at outlet. So this is the curve which is going up. Solidification melting hasn't started yet, and this is again the curve. So we'll wait for some time to check what will happen at the end of time steps. So the calculation has completed. So this is how the temperature which are been there as of now. We'll continue with this calculations further, and we'll check out what will happen at the end of 100 time steps. So we have completed around 1000 time steps. So as of now, the total temperature reaches to around 307. You can see the scale residual iterations, total temperature. So this curves which we are observing, then solidification melting. As of now, the melting hasn't started. Then we have total temperature again, contours of static temperature. Then here we have the contours of liquid fraction and the contours of total temperature. So this is various things which we have when available. So we'll wait for the further time so that we can visualize the solidification and melting. So we have completed around 3200 time steps. So at this time step, still with the temperature is 308.23. So it has to be run further in order to visualize the solidification and melting. However, we are observing a curve where the temperature curve becomes flats. So the modification, the variations are very little as of now, but it has to be done further. Or the another way is to try with the different cell zone condition where we are putting the source term. So if we are putting the higher value of C rate, probably we'll see solidification and melting. So by that time, this we have done it around 3200. So we'll end up with this particular iteration where the temperatures are reach around 308.23.